Hey students, and welcome to this first video about sampling distributions. Now, sampling distributions are essential for us to do inferential statistics. The first one we're going to discuss is the distribution of the sample mean. So let's dive in. So what is a sampling distribution? So first off, the sampling distribution of a statistic is a probability distribution for all possible values of the statistics computed from a sample of size n. So what that means in terms of the sample mean is that it's going to be a probability distribution of all possible values of the random variable x bar, which remember is the sample mean, computed from n from a population. And the population has a mean and a standard deviation that's known. So what that simplifies to is, suppose you have a large population of individuals. Well, if you select all of the possible sample size of, let's say, 10, so you grab all the different possibilities for 10 people from that population and calculate the average, which is the mean, for those 10 people in that sample, you do this over and over again, then you have the sampling distribution. So let's do a concrete example to make it a little clearer. So we have a population that's shown here. So this is a population distribution. So we have a random variable x that can take on 4 different values, specifically 18, 20, 22, and 24. And as you can see, they're all equal weight. So they're all 1/4 or 25%. And what you do is we're going to calculate the average or the mean of all of them to figure out what the population mean is. And then we're going to calculate the standard deviation for the population as well. And we've done these calculations before. So if we could figure out the mean and the standard deviation for this population, that's our starting point. Now, what we're going to do is we're going to look at a new random variable, which is the sample mean. So suppose we take sample size of 2. So what we're going to do is we have the observations of 18, 20, 22, and 24. Those are the population random variables that are allowed. And we're going to combine them in all the different possible ways. So as you can see, if we take the first observation as 18, the second observation as 18, then the sample of size 2 is 18, 18. And right here, if we take that value, these two values, and find the mean, we'll get 18. Now we can do it again for all of these other values. So 18, 20 would give us a mean of 19 for that sample size of 2 that we selected from the population, and so forth and so on. So all of these are all the possible ways we could select 2 individuals from the population. And then with those 2 individuals, we calculate the mean for that sample, and we put them on the inside of this table. So there are a total of 16 possible sample means because there are 16 possible samples. And we're going to sample with replacement, which means we put them back, which is why 18, 18 is possible. Now, after we've done this, let's take a look at what happens. So clearly we're going to end up with a different distribution. The goal here is to try to find the mean for the samples and the sampling distribution and see if that matches the mean of the population. And the reason that's really important is because we're really interested in the measures of center for a lot of quantitative values, variables. So with that said, we're going to talk about this thing called a point estimator. So a point estimator of a population parameter, remember, population parameter is for the whole population, this value exists, right? We might just not know it. So what we want is a point estimator that we can use on the sample data to calculate that single number as an estimate of the population parameter. So now if the sampling distribution has a mean equal to the population parameter, then it's said to be an unbiased estimate of the parameter. So what we're really looking for here is we're trying to see if this population mean on the left matches the sampling mean, right? On the right. So here you see 21 on the left for the population. And when we randomly sample with size n equals 2 things at a time, we also find 21. So therefore, if we have the mean of the sampling distribution or the mean of the population, that is the same value. So it is an unbiased estimator. Now notice that the standard deviation and then this thing over here, which later on we'll call the standard error, differ. And they differ by a very specific value. So we're going to get into that very, very soon. So the really cool part about this work is if a random variable x is normally distributed, then immediately the distribution of the sample mean is normally distributed as well, which means they both have that bell shape. They're both symmetric. Their highest point is where the mean, median, and mode all are. So all of the things we said about a normal distribution hold if the random variable itself is already normal. The amazing power that exists is with the central limit theorem, which says no matter how you start off, whatever the distribution is, remember we talked about a uniform distribution, that flat boxy rectangle, even if it starts like that, after a while, if you have a big enough sample, in this case, we usually say at least 30, we see it happening consistently, then you will have a distribution that is approximately normal, which is great because normal distributions we know a lot about. So let's look at this. So suppose that a simple random sample of size n we get from the population, and we're assigning the mean and standard deviation as listed here with the parameter symbols because it's for a population. So they're Greek symbols for the mean and for the standard deviation. Then the sampling distribution has the same mean. We just showed it was an unbiased estimator. And also this thing that I had mentioned called the standard error of the mean. And the difference between the standard deviation and the standard error of the mean is that we divide by square root of n. So there's this relationship where when you take the sampling distribution for the mean, it actually makes the graph thinner. So the standard deviation would be a bigger value than the standard deviation divided by square root of n. That'll make it a thinner, taller normal distribution. So also some other things we calculated before, the z-score we can calculate in the same way. The only thing that we do is we replace the mean with the mean for x bar, and we replace the standard deviation with the standard error of the mean. Same with new x value. If we calculate the x, we're multiplying by not the standard deviation, but the standard error. So really, for all of the normal stuff that we just worked through, the main change is that instead of just sigma or the standard deviation, we have sigma divided by square root of n, which is the standard error of the mean. So those are the big differences. Now, like I said, what's really cool about the central limit theorem is the following. So no matter what the original population is, when we get up to n equals 30, you'll see this normal distribution that's going to center right at the same mean as the original population. So here, the mean for the original population is in the middle of this rectangle. As you move over to n equals 2, it's more of a triangle. Starts looking normal around n equals 5. By n equals 30, it's definitely a normal distribution. And then we have some other funny looking distributions here. We have a bimodal. It has the 2 bumps. It's called bimodal. The mean is still in the middle in between the 2 bumps. And then as you can see, as you move over through the different sample sizes, eventually by n equals 30, you have a normal distribution. This one's an exponential. This one takes a little longer because it's very skewed. So if you have a strongly skewed population, it takes a while to get to normal. And if you start normal, you stay normal, it just gets thinner and taller, right? And that's because that standard deviation is being divided. So it gradually gets thinner. So across all of these, as you see, it centers on the mean, but loses some weight. And remember, these don't actually touch the horizontal axis. They get very, very close. We just can't see it. But at this point, many of the values are in a very, very thin area, which is very important for inferential statistics. So this last image here is critical. So if nothing else, remember that the mean stays in the middle across all of these various sampling distributions and the population. That's pretty consistent. And the standard error of the mean creates this the thinning out effect that you see across these different distributions. And as n goes to a higher number, it finally takes on the normal distribution curve shape as well. All right, so how do we calculate these values? So again, the mean of the sampling distribution is really easy. It's the same as the mean for the population. So 64 is 64 is 64. That won't change. But here we have the standard deviation of 18. We're going to divide that by the square root of n, which is 36 in this case. So that'll go from the standard deviation for the population of 18 down to 3 for the sampling distribution. So again, a much thinner graph. If we move on to the next one, again, 27 is 27, so that's the mean. And then again, the standard deviation divided by square root of n gives us a standard error of the mean. So that's just some calculations. And then all of the normal distribution stuff we did before hold. The only thing is, when you're talking about sampling distribution x bar, this will be your mean, and this will go in the place of where the standard deviation was. So instead of using standard deviation, you're going to use the standard error of the mean. So let's do one quick example. So here, let's suppose we have a simple random sample of 36 and the population mean of 64 and the standard deviation of 18. This should look familiar. It was in the one above. So we've already done some calculations. We've already figured out that the mean of the sampling distribution is 64 and the standard error of the mean is 3. Then what we can say is x bar. So that's the sampling distribution. Make sure you have that bar there. So it's for the means, not for the random variable. It's going to be approximately normal with a mean of 64 and the standard error holding the place here of 3. And then all calculations are the same. So let's show some calculations here. So first we need to put the mean in place. So we're going to do that. And that's going to go right there, 64. And then we need to use this 3 to give us our standard deviations first to the right. And then we can subtract 3 to go to the left. And that is what the distribution looks like. So we've taken the mean plus or minus the standard error here, which is in the place of the standard deviation. And we're looking at 62.6, which is roughly here. So we're going to shade in the area less than that. And that is what we're trying to find. So now we can use Excel again. So if you remember Excel for the normal distribution, it's equal norm.dist. We put in the value that we're going to go up to. So in this case, we're going to stop at 62.6. We need our mean and our standard error and true. And that will give us a value of 0.3204, which makes sense because we have about 13.5, let's say 14, 15, 16, and then a pretty sizable amount here. So upwards of 30, I would guess. So 32 makes sense. Using the empirical rule to guess what this should be roughly. So always use the empirical rule. It helps you get an estimate before you do the calculation. And this way, if you did the wrong side, you'll notice that it's too big or too small. Let's do another example. Again, the bottom stays the same for the horizontal because the value hasn't changed here for what the distribution is. So now 68.7 somewhere over here, we're going to calculate that area instead. And since this is greater than, we're going to need the complement because Excel is going to give us all this white space over here up to this line, not the green shaded area we want. So we're going to do 1 minus norm dist up to this value, mean standard error, and that will give us 0.0586, which sounds about right. This here is about 2.3. This is about 0.15 plus a little bit more. It doesn't go too far over to gain a lot on this side. So this seems to be about the right answer. Okay, last but certainly not least, what happens when we have an interval? So we're looking at 59 up to 65, roughly 66. So we're looking for that area. And again, Excel only gives us all the way through. So let's get this big chunk for 65.9 and then subtract off this little piece here that's white on the side. And we'll just do that by two norm.dist formulas in Excel. And then you're going to get about 65.6% or so, which makes sense. This, if it was in the middle here, that would have been 68, but we pushed it over a little bit, so we lost them because this is short. So it'll be a little bit less than 68. So 65.6% seems to make sense. So now one important takeaway is if we end up with a really small probability, we'll call this an unusual result for a sample, then that means one of two things. We happen to select one of the few samples that is not representative of the population. This could be sample bias or selection process or error. The other possibility is the mean for the sample is much less than the actual mean of the population. So unusual results may seem to indicate something much more than just an unusual result. So that's it for this video. I'll see you at sampling distribution for proportions in the next video.